All right, today we are going to be discussing the difference of in the means. It is helps us determine if the object of a study is statistically significant. So the difference in the means is literally just the difference in means. So it's when you subtract the means of two sets of data. So let me just write that. So it's when you subtract the means of two sets of data. Two sets of data. So it's usually what we consider like a control group and a group that actually was affected, or two different groups, but studying the same basic thing. And then what we do is we re-randomize them. It sounds weird, but we re-randomize them. It's basically just regrouping and mixing up the data without regard for the object being studied. So I'm going to try to explain that when we actually do the examples. It's a little hard to explain initially. So it's taking all the data. So you had two groups, you had two groups. One didn't get something, one did. You figure out their average, and then you mix them up and pretend like it's just one big group, and then separate them randomly. That's what regrouping is. So, and then mix them up. So after you've done your experiment, you then mix up the data and you pretend like it doesn't really matter who's grouped with who. So without regard for the object being studied. Okay, studies re-randomize and compute the difference of the mean. So you re-randomize them hundreds or thousands of times. So you take every person or every object, and whatever you were studying, you take that piece of data and you put it and you mix it up, and you don't care where it is. So hundreds and thousands of times. So that each element of data is paired with all elements at least once. So you're basically finding the average of all the pieces, all possible different ways. So to determine if the original data was unusual, or, here's the big one, statistically significant. Okay. So how do we use this information? Well, it's going to be used in a histogram or a dot plot. It's created to show all of the re-randomized results. So you take all of the results, all of them paired with all different ones, you subtract their means, and you put a dot on a histogram or a dot plot. The original experiment results are then compared to this histogram. Okay. And then based on the comparison, we can determine if it was statistically significant. And specifically, it's just a numbers game. Okay? So what you do is you count all of the values that were, here's what you do. So we have a normal curve. Okay, mostly they're going to be kind of looking like, or you have a histogram, or you have whatever, a dot plot. It has this kind of curve to it most of the time. Your original data, let's say, was right here. So you're going to add all of the data that was from this point over. Okay, or if your data was here, we're going to add all of those over. So you basically want the least number. You don't want to make it so that you have a huge amount. You want to make it so you have the least amount of numbers possible. Then you determine how many of those were at that value or greater, or at that value and less in either case. And if that value was greater than 2.5%, then it was not unusual or not statistically significant, or we also say inconclusive. Okay, not statistically significant. So if the number that you get, let's say it's 10.4%, that's greater than 2.5, then we can't tell anything about that study. The energy drink didn't do it, the fertilizer didn't take, whatever. Okay. If, however, we do the same exact thing and it's less than 2.5%, so we get the results that we got were less than that 2.5%, or it's an outlier, then we know it was statistically significant or unusual. So it was an unusual result, and so it was like, oh, this drink made a difference, or this whatever made a difference. Okay, let's do an example. All right, so I'm going to give you a second to read this. Okay. So I hope you took a second to read this. You have this study, and Ava thinks that the drinking energy drinks makes student read faster. So this one was the energy drink, and this one was the cola. Whatever. It says energy. It's EN. We have these means. Now, using this information from the experiment, explain why Ava's hypothesis may be incorrect. Well, we discussed this when we talked biases and things like that. So just based on her study, sample size is too small. 20 people, too small for an actual study to be useful. Okay? So that's the sample size is too small. Also, they asked for volunteers. Remember the word volunteer? Oh, I spelled that wrong. The volunteer. Okay, they tend to skew your study because if you only use volunteer, that's the word skew. I don't really understand why I can't write SKEW. It tends to skew your study because you're only getting a certain type of person, not everyone. And also, if you just read it, you're like, how fast did they read to begin with? Maybe they were fast readers to begin with. So, it's kind of skewed in that way also. I'm not going to write that because I'd probably screw it up. Okay. So how do we determine? So she's using these results anyways. She's re-randomizing them all together. And we want to determine if she did that 232 times. Okay, she re-randomized them all together. So what we need to do is determine, she says that it doesn't really matter, the energy drinks didn't really do it, didn't make anyone read faster. So how can we justify this? So what we do is we take the two values that we have here, the two means. We have 17.7 and 19.1. This is group 1 and this is group 2. We always take group 1 and we subtract group 2. Always in that order for consistency. So let's just take it down here. I'm just going to write those numbers. So the difference in the means is literally just subtracting those two. So it's 17.7 minus 19.1. And I get negative 1.4. So negative 1.4 falls about right here. Okay, negative 1.4 falls there. So we just count all these. This is 3, 2, 1, 2, 3, 2, 2, 5, 1, 1, 2, 1. Now that seems like a lot. It seems like a lot to me, but let's see what the percentage is going to be. So the percentage is 25 of the times were less than, doesn't really matter, 200 over 232 times. So what is this percentage? So this value that I get here is 0.10775. So the percentage is approximately 10.8%. 8%. So since this is bigger than 2.5%, it's not unusual, not statistically significant, or inconclusive. Unconclusive. These are all the words that we use to describe this. Okay, so let's do, nope, I went too far. Okay. So let's just look at these, take a second and read this real quick. Okay. So, all right, so we just want to determine statistically significant. And so what we're looking at here is we have two means, so figure out the difference of the means. So we do 12.9 minus 13.3, and we get negative 0.4. So find negative 0.4 on the graph. It's right about here. So anything lower than that, so this is about 22, about 12, about 2. You can just be approximate as long as you're not off the charts wrong. It will always work out. So it's 36 out of the 250. That percentage is, and then multiply that by 100. So that percentage is about 14.4%, which is a big number. So it's not going to be statistically significant. It's going to be inconclusive. So we just want to answer these questions. This is like a Delta math type question that you're going to see. Since the simulation shows many cases, because it was bigger than 2.5%, where the mean difference, so this is our mean difference, negative 0.4, or less occurred when the groups were re-randomized, it can be inferred that the mean difference in the study was very possibly due to the random assignment of participants into groups, so the results is inconclusive. So it was basically like the one group was just better than the other group to begin with, kind of thing. All right, so then we have the same thing with studying math or something. I don't know. I barely read these. Okay, but determining statistically significant subtracts the two means, the first group minus the second group always, so it's negative 12.5. Okay, so we find negative 12.5, there's negative 11, so this is right around here. So this is just 1 and 2, so this is 1, this is 2. Seems like there's not many, so there's 3 items out of the 250. So that percentage is times 100. So that percentage is about 1.2%. So that is way less than 2.5%, as I just said. So that's few cases where the mean difference of negative 12.5 or less occurred, okay? So it was very unlikely due to the random assignment of participants, meaning it was probably a good sampling. And it was definitely statistically significant, meaning it was a big deal. And it, whatever group 2 did was probably good. All right? I hope you all have a wonderful day. I'm sorry if it was long, but we're almost done. Have a good day.